Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to another episode of Stories from Space. I'm your host, Matt Williams, and today I want to address a topic that was suggested by a friend, and which is, of course, highly relevant. In fact, you might even say it's controversially related to the very notion of interstellar travel and whether or not humanity will ever be able to accomplish it. And so, the topic I'm referring to is none other than wormholes. Portals through space and time which have been predicted by the work of certain astrophysicists, not the least of which is Albert Einstein and Nathan Rosen. They've also become a bit of a pop culture staple, specifically with science fiction. For many fans of classical sci-fi, the concept of wormholes is certainly familiar. They constitute, essentially, tunnels through spacetime that allow us to traverse incredible distances without the need for a warp metric, and also, another benefit is that the transit time, we're told, would be instantaneous, or at the very least, very rapid. And this would allow ships carrying crews or robotic missions to traverse dozens or perhaps hundreds or even thousands of light years in a single jump. The concept is very familiar in the context of science fiction. After all, we've seen countless treatments of the idea. It has been used in franchises ranging from Dune and Star Wars and Star Trek, arguably the two biggest science fiction franchises of all time, to Battlestar Galactica and several popular video games, and of course film. But what exactly does the science say? Are wormholes even real? And can they, in fact, serve as a portal, allowing a spacecraft to traverse from one point in spacetime to another? And believe it or not, some science fiction franchises have attempted to explain how FTL travel works in their universe. For example, in Frank Herbert's Dune, we are told that the Navigators, a breed of mutant humans that are part of the Spacing Guild, for which every starship, every highliner in space depends upon, they use the spice, which they are constantly exposed to, hence why they've mutated, and this gives them a limited form of prescience, which they use to see through space and time, effectively charting a course that will bring the ship safely from one destination to another. However, it wasn't really until the sixth book in the series, Chapterhouse Dune, that Frank Herbert got into any of the technical details, and they were pretty scant. Essentially, the characters said that the Holtzman drives, as they're called, that they may in fact include tachyons, which at the time of writing, which was in the mid-1980s, was a theoretical particle that could, in theory, travel faster than light. However, that particular theory of tachyons, represented as superluminous particles, has since been debunked, and when physicists talk about tachyons today, they're referring to tachyon fields, which have to do with imaginary mass, not FTL concepts. However, it should be noted that Herbert, always the consummate genius, he truncated his explanation by indicating that, yes, in the future of the Dune universe, no one really fully understood how these drive systems work. They simply reproduced them, generation after generation, trusting in the Holtzman formulae, as they said. The franchise Star Wars, of course, includes hyperspace, but no attempt is made to explain how that works. How does a ship make the jump to hyperspace and travel faster than the speed of light? And some of what George Lucas wrote in the original movies that attempt to quantify how fast a ship can travel. For example, the Millennium Falcon. Han Solo says in a early scene in the first movie, A New Hope, that the Millennium Falcon can make 0.5 past light speed. And this really doesn't make any sense. Otherwise, it's treated with ambiguity and a suspension of disbelief, basically. Star Trek, on the other hand, did attempt to explain warp drives and warp travel, but kind of took a scattershot approach. And by that I mean, on the one hand, the Enterprise in The Next Generation, we learn that it relies on matter-antimatter annihilation. There's what's known as a dilithium chamber, which is somehow essential to the operation of the warp drive, and that the warp nacelles on every warp-capable spacecraft, that they have buzzard ram scoops at the front of them. And those would be the glowing things at the front of the engines, which apparently take in hydrogen fuel. So you've got a number of ideas here, two of which are based in real scientific concepts, an antimatter engine and a hydrogen spacecraft. And of course, there's references to the Alcubierre metric. Frequently in the show, it is mentioned that a warp shell is created by the warp core, which of course is what allows the Enterprise and other ships to achieve warp speed. Then again, the original series and all the spin-offs and follow-ups, they also attempt to quantify this by saying it's possible to achieve up to warp 10 or even more, and that time travel is possible if one were to exceed this barrier. Another example from popular culture in which FTL traveled through wormholes, where there's an attempt to explain it in scientific terms, is the sci-fi horror mashup Event Horizon. When one of the characters, known as Dr. Weir, explains the concept as follows. Use a rotating magnetic field to focus a narrow beam of gravitons. These, in turn, fold spacetime consistent with Weyl tensor dynamics until the spacetime curvature becomes infinitely large and you produce a singularity. Now, there's just one problem with this explanation. It's complete and utter gobbledygook. Gravitons are much like tachyons in that they are a theoretical particle that was proposed as a means of explaining quantum gravity. The idea there being that if scientists could find a quantum component for gravity, they could explain how all the fundamental forces of the universe fit together. As I'm sure we've covered in a previous episode, the four fundamental forces of the universe, this being electromagnetism, weak and strong nuclear forces, and gravity, only the first three have a quantum component. So, scientists still don't know how gravity fits in there on the quantum level. They know how gravity behaves, but can't yet explain why it exists at the quantum level. So when Dr. Weir says you send a beam of focused gravitons towards a point in spacetime, he's making things up. And, of course, that's why they call it science fiction. Weyl tensor dynamics, that's a real thing. That is a description of spacetime. However, focusing gravitons on a point in spacetime, what is being described there is, yes, essentially creating a miniature black hole, aka a singularity. Now, how this would give rise to FTL travel is not clear, and it exploits a lot of ambiguity when it comes to what we know about black holes and the possibility of wormholes. As for the whole idea of folding space, this is more a metaphor than anything else. Although, in theory, it does have some merit. It's the idea that if you interpret space-time as a two-dimensional plane, basically it's got a flat topology, it's got length, it's got width, but we don't see depth per se. And if it were possible to open up a wormhole, or to assume that wormholes naturally existed in space-time that connect one point in space to another, then yes, that by traversing that, you would be essentially folding space, because you would be traveling a huge amount of distance without actually moving the spacecraft. However, I do believe that this is more intended as a metaphor than any actual astrophysical prediction. And so, for very good reason, science fiction franchises, they have taken advantage of this theory, this unproven, ambiguous idea in physics, and used it as an explanation for FTL, much like the warp drive. There is no definitive way in which anything in our universe could travel faster than the speed of light, because it would violate causality, it would violate general relativity. We know for a fact, thanks to Einstein and the way general relativity has been tested 9 ways from Sunday, that matter cannot exceed the speed of light, or even achieve it. And black holes are a perfect visual reminder of that. As we covered in a previous episode, a black hole is essentially a collapsed star where the force of gravity on its surface, after it's collapsed to a certain radius, becomes equal to the speed of light. And consistent with Einstein's field equations, once the speed of light is achieved, then you no longer have time, because time dilates as the speed of light approaches, and if it were possible for the speed of light to actually be reached by an object, time would cease entirely. And so essentially, a black hole within its event horizon is essentially an object and a moment frozen in time. The gravity is so powerful, nothing can survive contact with it, and any information that falls into it. This includes all material that is accreted onto a black hole surface. It will be broken down right to the quantum level, and that information will be preserved for eternity. At least that was the theory until Hawking revealed that black holes emit radiation, aka Hawking radiation, and so that maybe over time they will lose that information, but it would take longer than the universe has existed or likely will ever exist. A good subject and one for another time. So, in the meantime, what does the science say about wormholes? Where does this theory come from? And as always, that requires a little bit of a trip down memory lane, a little bit of perusing the annals of history, and a lot of big names come up. For example, the first recorded mention of the wormhole as a concept occurred in 1928 when German mathematician and theoretical physicist Hermann Weyl proposed a hypothesis related to relativity, electromagnetic fields and matter, and the interconnected nature of it all, in which he proposed the existence of one-dimensional tubes. And his work went on to inspire American theoretical physicist John Archibald Wheeler, who coined the term in a 1957 paper that he co-wrote with an American physicist named Charles William Meissner, who is one of the authors on the seminal book Gravitation, and whose work also provided an early foundation for studies for quantum gravity and numerical relativity. In any case, they made what is believed to be the first recorded mention of the word wormhole, and this was in a paper titled Classical Physics as Geometry, in which they were attempting to describe unified field theories that accounted for gravitation, electromagnetism, and all other known forces. In the course of this paper, they said, this analysis forces one to consider situations where there is a net flux of lines of force through what topologists would call a handle of the multiply connected space, and what physicists might perhaps be excused for more vividly terming a wormhole. Now, what they were referring to were predictions and the many attempts at resolving the field equations of Einstein, which included the efforts of Karl Schwarzschild, the man for whom the Schwarzschild metric is named, and the Schwarzschild radius. And it was Schwarzschild's work, as we covered in a previous episode, that predicted the existence of black holes. However, his work also predicted the possibility of traversable wormholes. And Schwarzschild described these wormholes as an eternal black hole, which could be traversable from one point to the other, but only if it could remain stable. According to Schwarzschild's calculations, these wormholes would collapse too quickly unless there were exotic matter with a negative energy density present in the universe that could be used to stabilize them. And meanwhile, Einstein and Nathan Rosen, they came together to collaborate on a paper titled The Particle Problem in the General Theory of Relativity, released in 1935. And this paper was one of Einstein's attempts to disprove the concept of quantum entanglements, which he described as spooky action at a distance. In other words, a concept he did not care for. Using Schwarzschild's theory on black holes, he and Rosen described a bridge between two patches of space, where one end of the bridge was positively charged and the other one was negatively charged. And this, they believed, would allow pairs of particles and antiparticles to become entangled without violating the laws of relativity, and these became known as Einstein-Rosen, or ER bridges. A consequence of this theory, though, is that if particles are going to fall beneath the event horizon of a black hole and then traverse to another point in space and time along an ER bridge, there has to be a corresponding white hole in which the particles are then released. And another very interesting suggestion to come from this theory was that, in fact, ER bridges may not be connecting black holes from 2 points in space-time in the same universe, but in different universes. Which means, in theory, particles could be exchanged between universes all the time. However, a paper published in 1962, authored by Archibald Wheeler and Robert W. Fuller, they argued that a wormhole that connects two parts of the same universe would pinch off too quickly, and that anything traveling slower than the speed of light would not be able to make it through. Nevertheless, many physicists continue to maintain that wormholes could, in theory, exist. This includes Stephen Hawking and Kip Thorne. Now, Stephen Hawking needs no introduction, but his extensive work with black holes and his expertise means that he is more than familiar with the concept of Einstein-Rosen bridges, and he believed that it would be possible to stabilize a traversable wormhole. Kip Thorne, a noted astrophysicist and the consulting scientist for the movie Interstellar, he too has argued that not only could naturally occurring wormholes be stabilized, but has even argued that it might be possible to create one. And fans of the film Interstellar will no doubt remember that not only did it contain the first truly realistic visual representation of what a black hole would look like, which all came down to computations performed by Kip Thorne and his colleagues. But a key element in the story was the existence of a wormhole that allowed the crew to reach a distant star system. And the existence of this wormhole and how they described it, how they described the effects that the crew would experience going through it and what it would look like. Again, fans will recall it was spherical in shape, which was a deliberate choice. This all came down to actual theories proposed by Kip Thorne and his predecessors. In any case, it was in 1988 that Kip Thorne and Mike Morris, one of his graduate students, they independently came upon a theory that had been previously proposed by Homer Ellis, a professor emeritus at the University of Colorado Boulder, who in 1973 published a paper called Ether Flow Through a Drain Hole, a Particle Model in General Relativity. And as Thorne and Morris similarly argued in their paper, a traversable wormhole could be held open by a spherical shell of exotic matter, and this came to be known as a Morris-Thorne wormhole. Now, this term's come up a few times now, exotic matter, and what it refers to is hypothetical particles and states of matter that have not yet been discovered. And this includes a theory proposed by Einstein and Satyendra Nath Bose about a state of matter that was formed when a gas of bosons are reduced to temperatures nearing absolute zero. And these came to be known as Bose-Einstein condensates. And interestingly enough, in 1995, Bose-Einstein condensates were created in a lab by researchers from the University of Colorado Boulder. Another type of exotic matter that has come up was negative mass. And this is a hypothetical type of exotic matter, whose mass is essentially the opposite of normal matter. So much as antimatter is to normal matter, negative mass is to regular mass. And this too has been predicted, and physicists have yet to achieve the creation of particles that have negative mass. However, experiments are ongoing, and some of the results have been ambiguous, to say the least, which in science can be interpreted as a good sign. It's not a negative result, it is an ambiguous result, which means there could be a pathway to success. You just have to keep trying. And in addition to wormholes, the ability to create negative mass would also enable the creation of the Alcubierre warp drive. Because, as Miguel Alcubierre originally predicted in his proposal paper, negative mass and exotic matter would be necessary in order to create a warp bubble that would allow a ship to expand space-time behind it and contract it in front of it, thereby achieving faster-than-light travel without technically moving. So, exciting stuff, exciting potential. But as always, this remains in the realm of theory. So, could natural wormholes exist? In theory, yes. Could they be traversable, assuming, of course, you had the means to stabilize them? In theory, yes. Could they be created? Which is to say, could corridors between one area of space and another be created through the use of negative mass? Well, physicists like Kip Thorne do not rule it out. However, wormholes remain largely a thought experiment at this time. They exist only in theory because none have been observed in our universe. As Thorne himself wrote in The Science of Interstellar, we see no objects in our universe that could become wormholes as they age, which is a tangential reference to black holes. Because as we know, as stars age, they eventually exhaust their hydrogen and helium fuel and undergo gravitational collapse. And if they're massive enough, that collapse will be significant enough to form a black hole. And according to multiple lines of research by astrophysicists over the past century, it is possible that black holes are connected to other universes or other parts of our universe. And who knows, perhaps someday it will be possible for probes and spacecraft to investigate black holes more closely, to the point that we could actually confirm various theories about exotic matter and portals to other parts of the universe. But of course, this is not a question we can answer right now, but it is fun to speculate, and it is good to know that there is a theoretical basis for it. Because, of course, science fiction depends upon these ideas. As any fan of science fiction knows, the ability to traverse space, going from one star system to the next, visiting exotic planets, making contact with extraterrestrial intelligence, all of this is dependent upon the existence of some form of faster-than-light travel. Certainly doesn't apply to all science fiction. In fact, hard science fiction avoids any FTL concepts or any type of science that is yet to be proven or, based on the author's own discretion, likely to be proven in the not-too-distant future. In that respect, I would highly recommend an author who we covered in a previous episode, Alastair Reynolds, himself an astrophysicist. Most of his works take place in a universe where relativistic space travel is the only way that humanity is able to go from one star system to the next, and they do so using powerful drives that are able to generate constant acceleration, allowing them to get extremely close to the speed of light but never reaching it, and these are known as light hugger ships. A very clever term, in my humble opinion, though he too dipped into wormhole theory on occasion. And at the risk of editorializing a little, I, for one, do hope that the Alcubierre metric and the Alcubierre warp drive and that wormholes are a distinct possibility that lie in our future. And that if humanity does ever figure out the secret to exotic matter and negative mass, that we could enjoy all of these things. Especially because if we do find ourselves living in a universe where traversable wormholes do exist, but the Alcubierre warp drive doesn't, then creating stabilized wormholes, that is going to be very, very, very time consuming. Basically, you have to fly to a distant star system using conventional propulsion, which at this point I would hope would be very, very exotic and powerful, but it would still take decades or even centuries to get to some of the nearest stars, at which point the spacecraft could then go about stabilizing a wormhole, which would then be traversable and allow for FDL travel. But you see the point. Establishing these networks would take a very long time, but once created, would allow for humanity to not only become interplanetary or interstellar, but potentially intergalactic. And of course, that raises a whole bunch of other arguments. For example, if all this is possible, then why hasn't an advanced species done it already? Why haven't they populated the entire galaxy and are taking a peek at neighboring galaxies already? Because humanity does appear to be late to the party in any evaluation of the emergence of life in our universe. That, too, is fun to contemplate and speculate about. It gets into another favorite topic of mine, the Fermi paradox, which I've spoken endlessly about, so I won't do that here. And in another break from tradition, I would invite my listeners to comment on whether or not they think wormholes exist and whether or not we could use them for the sake of interstellar travel. Tell us what you think. Post it in the comments section. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.